Hi everyone. I think we can start. So I'm Anuprita More, and today I'm going to continue with this second lecture in this series of gravitational lensing. Yesterday you heard from Suril More about the basics and some theory of gravitational lensing, and so today I'm going to go into some more details and then talk about the applications of strong gravitational lensing. So let me get started. Yeah, so in gravitational lensing, we expect to see deflection of light rays from a distant source due to the mass of an intervening object. In strong gravitational lensing specifically, the source is sufficiently well aligned with the foreground lensing object that we can see multiple lensed images, as you can see here in this cartoon. So if you remember, the main observables in the strong lensing phenomena are the positions of the multiple lensed images, their magnifications, and the time delays. So let me revise some of these quantities which you learned about uh, some in some detail yesterday. But if you remember, you learned this lens equation yesterday while learning the theory. So what happens is that we have an observer and a lens in the sky plane, and there is a distant source S in the background, which can be in the absence of a lens, it can be seen at an angle, or you can imagine that the lens, the impact parameter between the lens and the source is given by this angle beta. This is the true source position, which cannot be seen. But because of the presence of the lens, this light ray coming from this source is deflected, and it appears to be coming from the position S1, which is given by the angle theta. So this is the image position angle theta. And so this lens equation basically allows us to relate these angular image positions, the true source position with the image position, with the help of this angle alpha, which is called the scale deflection angle. And it is related to the true deflection angle alpha hat through this simple relation. And with the help of this, once you specify the properties of the lens object, which could be a galaxy, along with their distances, we can solve this lens equation, and we can determine what is the unknown source position. Just a reminder that all these angles that we are talking about, these are two-dimensional vectors. These distances are angular diameter distances. And generally speaking, in strong lensing, the true source properties, here in this case, the position is generally unknown. And so all the quantities that we are measuring, these are going to be relative quantities. So from the observations, what we can measure are the relative image positions. So let me show an example of a gravitational lens. This is an image taken by the Hubble Space Telescope. What you see here at the center of this image is a massive galaxy. This galaxy is a part of a galaxy cluster. As you can see, there are multiple other yellowish galaxies which are members of this massive galaxy cluster. And what you can also see are the multiple lensed images of a distant quasar. So what you can measure from this kind of observation data, you can get the angular separation between the various images and the lens center. We just, as a matter of convenience, we just choose the lens center as our origin, and so we can measure all these theta 1, theta 2, theta 3, theta 4. These kind of angular positions can be measured. If we can get spectroscopic data and the distances to the foreground lens and the background source, then we can solve this kind of lens equations, and we can go through various models for alpha of theta and get determine what is the unknown source position, and also get constraints on the this kind of model that goes into generating the alpha of theta. So this is mainly about the image positions. Next, you have heard about magnification. So basically, what happens is that if you have a circular source, then via this Jacobian matrix, you can map this source into the image plane, and you can tell how this source will be modified because of the lensing magnification. So if there is isotropic scaling, then it will just look like a bigger circular source. But if there is a possibility that there is presence of shear in the lensing galaxy, and that causes an isotropic magnification. So you can see more magnification in one direction compared to the other. Now, since these quantities have these are these two-dimensional vectors, these Jacobian matrix have their eigenvectors, and based on the eigenvalues of these vectors, we can divide the lensed images into three types. So these are called type 1, 2, and 3. And in general, so suppose the source looks something like this. Then based on the eigenvalues, if both the eigenvalues are positive, then the type 1 image is the one where these both eigenvalues are positive, and the image, this image that is of type 1, will look very much like how the original source is. If both the eigenvalues are negative, that means then the source flips its sign along the direction of the eigenvectors. So when both the eigenvalues are negative, it flips along both the directions, and then this is how the image would appear. And so this is the type 3 image. In case of type 2 image, only one of the eigenvalues is negative, so the image of that source appears to be flipped in only one of the directions. So these are the three types of the images that we expect to see in strong lensing. And in very simple terms, one can say that magnification is given by the image area over the source area. So here I want to show just one example of another galaxy cluster, where you can see this beautiful spiral galaxy, which is located in the distant background, which is being lensed. And you can see that there are multiple images. This is let's say the first image, which is pretty much similar to how the original image of the source spiral galaxy looks like. And here you can see additional images which are distorted and magnified in different ways. So here you can see there is an isotropic scaling happening. There are furthermore images which are located here. It's somewhat difficult to see the flipping of the image here, but if you take a look at this particular reference, you might get an idea of how some of these images are inverted versions of the true source that's shown here. All right, and now the third observable is the time delay. Again, you learned about this time delay function and how the time delay depends on is affected by two factors. One is the geometric time delay, and the other is based on the gravitational potential. Again, to remind that all of the quantities that we can measure are the relative quantities. So we cannot really measure the time delay between the unperturbed ray coming from the source versus image one. We cannot really measure that kind of time delay, but we can measure the time delay between two lensed images. So I've rewritten this equation here, which gives the relative time delays between two images, theta I, theta j. And there is also a dependency on this distance ratios. So via this dependency on the distance ratios, we find that if we can measure the time delays, then we can get constraints on the Hubble constant, because the distance, angular diameter distance, is inversely proportional to the Hubble constant. And so systems where we can measure the time delays, then after detailed modeling of the system, we can get constraints on the Hubble constraint. So here I'm showing an animation which comes from real data. So on the top panel, we are seeing images of a lensed quasars, and we can see there is some flickering happening in various images. Some images are getting much more brighter versus the others. And in the bottom panel here, we are looking at the light curves for all of those images, 4 images, A, B, C, D. I will play the animation again, and you can see that uh, there are certain features in these light curves. So there is somewhat flickering, and then there is a sudden brightening. So there is this sharp increase, which is visible in each of these light curves, but after a certain time delay. So one can match these various curves and get the accurate time delay between various images with respect to, let's say, image A, and that allows us to better understand these systems. So another interesting thing to note is that if you look at these arrival time surfaces, so let's say we are looking at this source here in the absence of a lens. So here L stands for low, which means the minimum. So if you look at this arrival time surface, also known as the survey, which we can get from the Fermat potential. So in the absence of the lens, what we are seeing is the image that is seen directly. And as you introduce a lens in the foreground, you can see that these contours are getting distorted. And when the source and the lens are sufficiently aligned, then we can see additional pairs of images being formed. The image that is labeled as S here, this is the type 2 image, which is formed at the saddle point. And then H is stands for high, which means maximum in this time delay surface. So these images, they are formed at the stationary points of these time delay surface, and you can see that also very clearly from by taking the gradient of this time delay equation shown here in this previous slide. Uh, the gradient of this equation where it goes to 0, that's where the stationary points are, and that's where the strongly lensed images are formed. And again, these are the different types, 3 types of images, which I mentioned earlier, type 1, type 2, type 3, which are the minima and the saddle point and the maximum. Another interesting thing we can see from these typical lens systems that are found in for galaxy scale lenses. So there are certain special situations that we can analyze. So if you look at this Jacobian matrix, if you take the determinant of this matrix, there are locations in the lens plane where these determinant values go to 0, and these colored contours show exactly those locations. These are called the critical curves. This is in the lens plane or the image plane. If you map them back to the source plane, then this is how the contours look like. You can see various colored sections are mapped to specific, the same colors here in the source plane. In the source plane, these contours are called caustics. There are some interesting things to note here, marked by like 135. This represents the multiplicity of the lensed images. So if the source, so again, for reference, the lens center here is at the location of the center of this image. And suppose the source is sufficiently far away, which is outside these contours, then that's where you will see the source having a single lensed image, and that's what we mean by 1. As the source starts to be further and more aligned with the lens center, as it crosses these caustics, the number of images increase, and when the source is inside these outer caustics, we see 3 images. and as the source crosses further the inner caustics, then we see 5 images of the same source. So this is what we expect typically for lensing galaxies, which tend to be elliptical. This is another version of the similar idea. Here, now we are showing the source actually moving at different locations, and you can see that the magenta source is currently located in the.
Can you please explain what is meant by this caustics? Caustics. Um, what is?
Yeah. So what I was saying is that if you look at the magnification matrix or the Jacobian matrix, which allows us to determine the magnification at each and every point here in the image plane or the lens plane, then the location where the determinant of this matrix goes to 0, those are the points which are called the critical curves, which are shown here with these colored contours. And if you map them to the source plane, if you map these colored contours to where they are located in the source plane through the lens equation, then those contours in the source plane are called caustics. Does that answer your question?
Okay. I thought that is there any geometrical significance, say physical, say, in the image itself. I mean, okay, I think you are going to explain it.
Yeah, so if the source is located here sufficiently far away, then you can see one image, one slightly distorted image of the magenta source. And as you go closer to these caustics in this region, which is marked with the label 3, where we expect to see 3 lensed images. So that's shown by this sign and the dark blue color. Then you can see how the corresponding lensed images look like. Okay, and when the source is much closer to one of these caustics, right, this would mean that the magnification, the corresponding lensing magnification is going to be extremely high. And so that's where we can see this green arc-like structure, which means the images are extremely distorted in certain directions, and the magnification is extremely high. Yeah, I hope that helped. And this another cartoon is just different angle through which the source is moving, and then correspondingly what kind of images and their shapes, how they would look like, are shown in this second panel here again. So I want to talk about a couple of uh, models that are analyzed or studied typically for different types of lenses and what we expect to see in such cases. So one of the simplest model to consider for the lens is a point mass lens. In this case, the scale deflection angle is given by this expression here. And now if you substitute this scale deflection angle into the lens equation, this is how the lens equation looks like. And you can see that it is the alpha is just alpha just depends on theta. I have just rewritten this term here as theta e, which is shown here again explicitly. So so in this case, what we can do is that without any loss of generality, we can align our frame such that we are these angles or these impact parameters in the lens plane, they are aligned with the x-axis, and so this reduces to one-dimensional vector. And then what you will find is that for a specific case where beta goes to 0, meaning the source is perfectly aligned with the lens. So in this case, the source would be right behind this particular lens. In that case, you will find that this equation has only one solution, which is theta e, which means that all the the images that are formed at a distance of theta e, or an angular separation of theta e. So you will see this kind of a ring. So I'm showing this image, even though this particular lens here is not really a point mass lens, but this is sufficient for showing the example of how the Einstein ring looks like, where the source is sufficiently well aligned with the lens. So if you solve this equation, you what you will firstly notice that this becomes a quadratic equation, and then this equation has two solutions given by this theta plus theta minus, and so uh, and then if you learned about this Jacobian matrix in the last lecture. So that's given by this del beta by del theta. So if you apply that to this lens equation again, you can then derive how the magnification will look like. So in this point mass lens, we basically have two solutions, and so the images, the positions of the images are given by this, and the magnifications are given by this expression here. A side note here, if you look at this particular Einstein radius, yeah, I forgot to mention that this kind of ring that is formed is called an Einstein ring, and then the radius of this ring is called the Einstein radius. So if you just look at the scales of various quantities in this Einstein radius equation, then there is something worth noting here. So, for example, if you consider a mass of the order of our sun, so one solar mass, and distances that are of the order of a kiloparsec, then what you will find is that the Einstein radius, or the angular image separation that we expect, is of the order of milliarcseconds. And so you can see how small the deflection is if the lens is something similar to our star. And so no wonder when Einstein looked at these sort of numbers, he thought that the amount of this deflection is extremely small, and it's going to be really difficult to measure this in the observations. But now, if you increase the scale of this systems, so instead of looking at a single star, if you look at a whole galaxy, which is significantly much more massive, and if we talk about extragalactic distances, which is of the order of gigaparsecs, then the deflection produced by such massive lenses are of the order of 1 arcsecond. So 1 arcsecond is also a small number, but it is something that is achievable by current telescopes. All right, so moving on from the point mass lens to the extended mass lens. So this is what we typically see in galaxy scale lens systems. So these are the images of typical lensing galaxies, which are early type elliptical looking galaxies. And these are usually well fit by an isothermal profile, where the three-dimensional density profile is given by 1 over r squared. So I'm considering a simpler scenario here. I'm considering this to be a spherical system because that is much more easily, it is much more easy to calculate all the lensing observables for the spherical case. Even though this is somewhat a simplification, but let's just go through this. So the three-dimensional density profile is given by 1 over r squared, and the mass in these systems scales as r. So if you look at the rotational velocities, the rotation curves, they look flat in these systems, and so they are basically constant. And the two-dimensional surface density profile is then given by this. And if you substitute this surface mass density profile in the scale deflection angle this expression and do the integral, and what you will find is that the scale deflection angle is now a constant value which only depends on the velocity dispersion of these galaxies. And then the corresponding Einstein radius looks like this. So this is interesting that for this, if you choose a model for the lens as a singular isothermal sphere, then you will see a constant deflection angle. And so again, now if we take this scale deflection angle and substitute in the lens equation, you will get the solutions to the lens equation, which are then given by this expression. So for all the source positions which are within the Einstein radius, where you will see multiple lensed images, the locations of the images, they are given by just the source position plus or minus the Einstein radius. And similarly, as before, you can take the Jacobian of the lens equation for this particular case, and you will find that the magnifications are then given by this expression. So this SIS kind of model is a similar model. Generally, for galaxy scale lenses where we see ellipticities, we include ellipticity in this model, and that makes these calculations somewhat more complicated. But these are still something that we can calculate, and this is something that is often used in analysis of strong lens systems. So let me move now to the applications, talking about how these lensed observables are analyzed and what kind of quantities in the lensing community, what kind of quantities we try to measure or get constraints on. So one of the most important things that we can learn from strong lensing are the properties of dark matter, because lensing is insensitive to the type of the matter that's there in the universe. And as you know, that dark matter is one of the it is the most dominant component in the matter budget of the universe. And this is one of the best. Strong lensing is one of the best methods to get constraints on dark matter properties. So if you remember from these various lensed observables that we talked about, the image positions, the magnifications, and the time degrees. So let's start with the image positions. So if given a lens system where you can see the image positions, if you can measure the distances to the foreground and the background, and then you can measure the Einstein radius of the system, the Einstein radius will allow us to get measurement of the total matter that is enclosed within the multiple lensed images. And so there are various studies in which these quantities are measured, the image positions and the distances are measured, and even not just for one system, but a large sample of lens systems are then analyzed, then to get idea of how much matter, total matter is enclosed within that aperture, within the Einstein radius. And there are other methods that are used to, let me just show with this example. So with strong lensing, what one can get is the total matter that is enclosed within this sort of a ring. And based on other observations, we can quantify how much mass is enclosed, how much mass is distributed in the stellar population. And so whatever is the remaining matter is the dark matter. So this total aperture gives us the total matter, and then the mass that is in the light profile, in the light component, is given by the stellar mass. And so if you just subtract the two masses, you can get an idea of how much dark matter there is in these systems. So I'm just showing a few plots from various studies here, where the fraction of dark matter within these strong lensing galaxies are measured. Here, for example, as a function of the mass of the lensing galaxy. Here it is shown as the radial distance, as a function of the radial distance. So as you go from the center of the lensing galaxy to the outskirts, how the fraction of dark matter changes. This is another study, again done with a heterogeneous sample of lens systems to quantify the fraction of dark matter as a function of the radius. And we can see that um, the fraction of dark matter depends on the radius of depends, means it's a function of the radius of the uh, galaxy. And another quantity now you can measure is not just the total matter that is enclosed, but also how this matter is distributed. And for these kind of studies, these are again we make use of strong lensing, where we can measure the mass within a certain aperture, usually that Einstein ring, and that is then complemented with other measurements of masses. For example, we can use the kinematics of the stars which are there within the galaxies. For some of the nearby galaxies, we can measure how fast the stars are moving, what is the velocity dispersion of the galaxies, and we get an idea of the mass of these based on the stellar kinematics. We can get an idea of another mass at a different radial distance, and that way we can probe how the mass is distributed at different radial distances, and that allows us to get an idea of how the mass is distributed within a galaxy. So not just the total mass, but also how the dark matter is distributed in these galaxies. And so here are a few plots which are showing studies which make use of, again, very many strong lenses. For example, here these constraints are shown for a sample of strong lensing galaxies, where a power law profile is assumed for the mass distribution, and then what they find is that on average, galaxies, they are close to isothermal profiles. And this is a different study where statistical quantities are used for constraining the mass distribution. Sorry. I'm sorry, I'm not able to hear properly. Maybe you can leave your question in the chat. Okay, let me continue. So, yeah, here in this case, we are showing how the mass distribution looks like, but we are looking at much more massive scales, and we are making use of statistical quantities. For example, we are looking at the Einstein radius, you can say, or let's say the Einstein radius, and what we are asking is, if you have a systematically compiled sample of strong lenses from a survey, what would be the distribution of the Einstein radius found in the entire population? And that depends on what is the mass distribution of your lenses. So in this case, we are going to much more massive scale. So instead of galaxies, we are looking at groups of galaxies which are acting as lenses. And here, here the magenta points are coming from these are coming from the data where we have measured the Einstein radii of a population of group scale lenses, and we are we are comparing them to different model predictions. So if your model is more like the isothermal profile, or whether it is something else, how would the image separation or the Einstein radius distribution would look like, and we are able to then constrain one particular model for the mass distribution of galaxy groups. In this case, here we are showing for one particular system, this is a massive galaxy cluster. The image of this system looks like this. Here we have these four images, but then much deeper data allows us to see that there is another, like the fifth image, which is very faint, but very close to this lens galaxy here. This yellow galaxy is the lens galaxy, and there is an additional image very close to this galaxy. And with the help of the observables here, the positions of these lensed images, their magnifications, and also the time delays in this case, because this is a lens quasar, so we can get the time delays as well. Various mass models are tested, various mass models for this galaxy cluster. For example, this something called the NFW profile is tested here, and it is then compared with the observations, and that's how we are able to say how the dark matter is distributed in these very central regions. Here, very central regions of this galaxy cluster, thanks to the presence of this fifth image that is seen. So another application of dark matter, application of strong lensing to get constraints on dark matter is via looking at perturbations to these observables. So far we have talked about measuring the image positions, their magnifications, and their time delays. But if there are some very low mass dark matter, what are called subhalos or substructures, and if they happen to be present very close to one of the lensed images, then they will cause additional deflection due to gravitational lensing, and they will cause perturbation to these observables. And with the help of these measurements to these, so here in this case, they are looking at perturbations to the relative magnifications of a sample of gravitational lenses, and they have tried to quantify what is the amount of dark matter which is there in these subhalos, such that it can fit the observational data. It can fit the observation data where we see these perturbations in the relative magnifications. So here they have shown this plot where these two lines here enclose the range where we expect to see, or the amount of substructure we expect to see from the standard cosmological models. That's shown by these vertical lines, whereas the data is shown by these contours, which is somewhat consistent with the current model for the cosmology. And similarly, this particular analysis was based on perturbations due to the magnifications. There are other analyses also done where we are looking at perturbations to the positions of the images. So this is called Astrometric Anomaly, where we look at how the subhalos distort the positions of these images, and again we can make use of different models which then allow us to quantify how much matter is present in these subhalos, such that you will see some given effect in a given lens system. And this tells us that if you have a large sample of lenses where you have some model for the subhalos which are distributed in some manner within these galaxies or clusters, then by looking at these perturbations to the positions of the images and making a model and testing these various models, we can then put constraints on the mass function of these subhalos, meaning how many halos of a certain mass are expected to be found in galaxies or clusters and so on. So this kind of plot shows the possibility that one can put constraints on the subhalo mass function. Here, this particular study talks about how by taking individual galaxy cluster, because galaxy clusters are so massive and their lensing cross section is also so large, that you can have several tens of background sources being lensed at once. And so you can see many families of distant sources and their lensed images, and you can analyze all of these together and generate this kind of a map which shows the dark matter distribution. So these all these peaks that you're seeing, these are the locations of the dark matter subhalos within a galaxy cluster. So by analyzing these rich strong lensing galaxy clusters, you can build this kind of distribution of the subhalos population within the galaxy cluster. And again, we can get a constraint on how the subhalo mass function should look like. You can again test various cosmological models, because as you change your cosmological parameters, you expect to see a change in the subhalo mass function. There are certain cosmologies which will predict very small amount of subhalos, very small numbers of subhalos. And so with the help of these kind of observations, we can test whether the standard cosmological model is consistent with the data or not. Now, talking about the using magnification as a means of studying very distant, faint lensed galaxies. So with the help of the lensing magnification, we can use these strong lensing systems as natural telescopes, and we get a zoomed version of very distant and faint galaxies. The kind of things that we can study from these distant galaxies are their stellar population properties, for example, their luminosities, stellar masses, the formation rate of stars in these systems, how much metallicity is there in these galaxies. Remember that when we are looking at these distant galaxies, we are also looking at the galaxies at their how they look like in their at the young stages of their life cycle, right? How they look like when they were very young, early in their formation of these galaxies, how these galaxies look like, and how the stellar population properties were like in these systems. And we can then compare them with the local understanding, local observational data we have on galaxies in the nearby universe. And so I'm just showing this one example again, where there's this one galaxy cluster where a distant spiral galaxy located at a redshift of 1.7 is being highly magnified. The magnification factor, which is obtained from the model of the system, is about 42. So you can see there is extreme magnification happening. You can see that these even by looking at these giant arcs, we can see there is strong distortions. The size of this arc itself is extremely big. It's roughly 40 arc seconds in the sky. And here, what you can see here in the inset is based on the lens modeling, they have reconstructed how the true source might look like, and that's what you're seeing here. And as you can see, it's very messy, because early in the formation of these galaxies, there is a lot of star formation happening, and one tends to see mergers, one tends to see different sites where star formation is happening. So it doesn't look like a nice smooth light profile. but you can see various clumps and knots and various features. So this particular galaxy, when the lensed galaxy, when it was further followed up by these Sharon et al. And White et al. Team, what they studied here is that they looked at the velocity dispersion, they looked at the age, metallicity, and so on. And what they found is that there is a tidal tail that's being seen here, so there is some sort of merger happening. There are different clumps here, which some of them are gas rich, some of them are poor, they have low metallicity, and they could quantify the sizes of these regions, sizes of these clumps, and many other things. So you can see how rich these kind of systems can be, and how much we can learn about some very faint galaxies with the help of strong lensing. In this case, here I'm showing how lensed quasars can be used to study the properties of the black holes, which are located at the center of these galaxies. So we expect that the masses of the black holes may be related to the properties of the host galaxies themselves. So there are these relations which are constrained from the nearby universe. For example, the relation between the black hole mass and the luminosity of the host galaxy. And these kind of relations can generally be fitted to the data in the from the observations from the nearby or intermediate redshifts. But with the help of lensed quasars, since we can see very distant sources, very distant quasars, we can study these sort of mass luminosity relations for the black holes and their host galaxies at a much higher redshift. And that's what's shown here in this plot. So now coming to more of the time delay based science. So if you remember, I mentioned that the time delays, because of the dependency on the angular diameter distances, one can get constraints on Hubble constant. And so most of the time delay based studies are, their main interest is in constraining the Hubble constant by measuring the time delays in these systems. So initially, in Refsdal in 1964, he thought about observing lensed supernovae and making use of their transient nature to measure these time delays, such that one can put constraint on the Hubble constant. However, as you know, the supernovae, they are transient in nature, and the rate of supernovae is not that not that high. As a result, there are not that many lensed supernovae that are known in the literature. But instead of lensed supernovae, what the lensing community has managed to make use of are the lensed quasars, because the quasars themselves are variable sources, and they are not transient. So we are able to see many more lensed quasars than lensed supernovae. Although in the recent few years we have detected a few lensed supernovae, and that's extremely exciting for other reasons also. But I won't go into that right now. You can ask me later. So these lensed quasars have been studied much more extensively and in much more detail. There are various collaborations like Cosmological, Holy Cow, and we can look at some of these papers where to see what kind of analysis they have done. So here are some examples of the lensed quasars which have been studied in these collaborations. They monitor these systems over several months and get very accurate measurements of the time delays. There are other follow-up observations done also to accurately measure the distances and other quantities which will allow us to better model the lens system itself. because if you let me just show the slide for the time delays. If you want to measure cosmological parameters, if you look at this lens equation, then um, time delays, which are on the left hand side, these are the observables. Uh, we need to measure these very well, but then we also need to quantify this component, which depends on the lens model itself. So if we can, if we get a good hold over this quantity and the time delays on the left, then we are able to very well measure these cosmological parameters via the angular diameter distances. So measuring this part is extremely important, and that's what these collaborations put a lot of effort in, um, and that's how they are able to get sufficiently good precision on the measurements of the Hubble constant. And here are some one plot from one of their papers. There are, I think, there are many more new results which you can look at from this collaboration. I want to quickly just mention, apart from just these observables directly, we can look at a sample of lens systems, and with the help of statistical observations we can also measure certain properties. Either we can constrain the cosmological parameters, or we can get constraints on the model of the lens itself. For example, if we look at just the abundance of giant arcs that are expected to be found in the universe, the presence of these giant arcs depends on presence of clusters. And since clusters are very few in number, how many clusters you expect to see in the universe depends sensitively on the cosmological model and their parameters. And so with the help of these abundance of giant arcs, one can there is a way to get constraints on cosmological parameters, which was pointed out in this paper. There are other studies where statistical samples of lens quasars were used, and they looked at the image separation or the Einstein radius distribution. And again, it was shown that if you vary the cosmological parameters, for example, here the dark energy, then the expected distribution can look different for different models. And if we are able to measure this from the observations, then we can constrain these cosmological parameters. Um, so I don't know how much time is left, but very quickly I want to point out. Let me see how much time I have. Just a few minutes. Okay. So very quickly, I want to point out that there are these special lens systems where instead of, so in a regular system, we have the observer, we have the lens, and then we have a single source in the background, at least for a galaxy scale lens system, that's how it is. But we we can be lucky, and some even more rare instances, it can happen that instead of a single source in the background, there's a second source, which also happens to be sufficiently well aligned. And these are kind of systems are called double source plane lens systems. And there is an interesting thing happening in these kind of lens systems. If we assume simplicity of the whole situation, and simplicity of the lens model, then we can show that by looking at the Einstein radii of source 1 versus the Einstein radii of source 2. So that's the theta 1 by theta 2. If we can take the ratio of these Einstein radii, and under the assumption that the lens model is simple enough, then we can show that this kind of ratio of these Einstein radii, which just depends on the distance ratios, we can show that this is sensitive to some of the cosmological parameters, like the dark energy parameters. And if we can find sufficient number of these double source plane lens systems, then we could get good constraints on some of these cosmological parameters. which is complementary to other probes of cosmology in the literature. Okay, so I would like to stop at this point and take any questions. So if there are any questions, feel free to raise your hands. Okay, so there is a question on the chat, so I'll just read it out. Do we have double or multiple lens systems? Uh, does so is your question referring to double lens galaxies, meaning the foreground lens being double? If you want to explain your question, we can unmute, I believe. Okay, anyway, I will assume that the question is about can we have double lensing galaxies in addition to the double source lenses, double source plane lenses that I referred to here. So if that is the question, then yes, it can happen that instead of a single lens galaxy, we have more than one lens galaxies here. Or what can also happen is that this source one, I hope you can see my screen, this source one here itself is massive enough that it can act as a lens to this background source too. So these are very much possible, and in fact, I wanted to show here, but I could not explain earlier. But this particular lens system is very much like that. We have a lens galaxy here in the foreground, which looks like this yellowish elliptical galaxy, and then we have this red arc, which this red arc, and then a counter image here that corresponds to the source one, and then we have the source two, which is this bluish, almost like a ring that is seen which is at a higher distance, and we can see that the Einstein ring is much bigger compared to this red arc. When we analyzed this particular system, we found out that this in this particular lens system, it is not exactly double source plane system. It is also double lens plane system. So the source one is massive enough that we need to account for its presence at a different redshift compared to the lens plane and the main lens in galaxy. So we not only model the mass distribution in the lens plane, the lensing effect from the main lens plane, but also lensing effect coming from the source one plane. And once we take into account these two mass components, then we are able to reproduce this Einstein ring and many of its features. So there are instances where you can have double lenses and or double sources. Okay, thanks. One question that I saw earlier was, how can you confirm that those light spots are just multiple images of the same quasar and not multiple real sources? Yes, so as I was saying, is that in many instances, or many of the lens systems that we have to study, we have to get spectroscopic redshifts for these or the distances to these systems. And when you measure these spectroscopic redshifts, what you find is that the redshifts of all of these features, they are identical. So that allows us to be confident that these are same sources. There are other ways also. There are, let me see if I have examples. Like in this case, if you are seeing a spiral galaxy here and then another spiral galaxy which look very much the same, so there are certain features that you can see which look just distorted versions of the others, then again it is clear that these are lensed images. But measuring the spectroscopic redshifts, it's a much more like quantitatively robust way of stating that these are counter images of each other. Also, if we are looking at the time delays, if you can clearly see there is sudden there is sorry, there is a certain pattern in the light curve of one of the images versus the others. If you are seeing similar brightening and dimming after a certain time delay, that also indicates that it is the same source. Otherwise, we wouldn't really expect similar features to appear in the light curves. Um, okay, so let me take another question. So there is one question where Shubhadeep is asking, we have discovered the optical image of Sagittarius A black hole by Event Horizon Telescope, but why we cannot detect it by gravitational lensing? What is the limitation of this technique? So, firstly, let me say that black hole is massive enough or dense enough. It has almost like it has infinite density, right? So anyway, the point is that it is massive enough and dense enough that uh, any light that we are seeing in these observations by the Event Horizon Telescope, it is being deflected, it is being lensed by the black hole. It's just that the kind of lensing that you are seeing is different, or the kind of features that you are seeing are different from the instances that we are showing you, because the distance of the distances involved between the source, what you call the source, and the lens those distances are very large. Whereas in this case where we are looking at the black hole in our own galaxy, the light source uh, is just, it's right next to it, is in the vicinity of the black hole itself. So based on where your source of light is located, and how you can model the lens, the kind of lensing effects you will see will be different. And so we are seeing the lensing effect, but we are not seeing it exactly the way we see for galaxies, uh, where there's a galaxy in the foreground and a quasar or another distant galaxy in the background. Those effects look different, just because of the different properties and the different distances. Um, okay. Are there any more questions? Okay, I don't see any more questions here. Maybe they are there on the YouTube channel. In case they are, I could answer them later in the chat. So I can think at this point I would like to then end this session here. So thank you for joining this second lecture in the series of gravitational lensing. And yes, I think Santosh wants to say something. Okay, sure. So meanwhile, what I wanted to say is that so tomorrow is going to be the third lecture in this series. Third lecture in the series. I think Surud is going to talk about weak gravitational lensing. So that is another interesting domain. It's very different from what you see for strong lensing. It's not as beautiful, but uh, nevertheless, it is a very interesting set of observations and allow us to uh, model the mass distributions on much larger scales than we can achieve with strong lensing. So you'll get to hear more about that, I believe. So the question that was there on the YouTube channel was, what do you mean by putting constraint on the Hubble constant? What I mean by that is just measuring the Hubble constant. Um, there are other methods in the literature where they measure the Hubble constant, and putting constraint just means that we have some prior knowledge about what the Hubble constant is like, but now we want to measure it further, more accurately. And so, with the help of these time delay based lens systems, we can measure or constrain where what the actual value of the Hubble constant is much more accurately. Um, yeah, that's all I guess. So I think that's pretty much all. So thanks everyone for joining, and I hope you guys will join tomorrow for the last lecture in this series. So thanks everyone. Thank you. Bye.
Thank you, Anuprita.
Thanks.